So this video is just a continuation of our infinite well. Just to remind you, the last time we got the eigenfunctions for the infinite well, we got the eigenvalues for the infinite well. We also calculated the average position for all these states. They're all at L over 2. And then we also did x squared, but when we did the uncertainty in x, just for the first state, for this one up here, it was 18% of the box. That was the plus or minus 1 standard deviation. And we said these are the eigenfunctions, but if you haven't measured it yet, it's a combination of all of these right here, where the alphas are the probability of measuring those values, of measuring these energies. Okay, so now I wanted to say, what about the average momentum? What is the average momentum of that particle? Remember, the momentum operator was minus I h bar partial with respect to x. So if we wanted to get the average momentum, we would just integrate right here. We're just using our formula right here. We just put the momentum operator right in the middle. It has to be in the middle, so we get our psi x times minus I h bar partial with respect to x of, this was the star, psi of x dx. Okay, again, the star doesn't matter because our wave functions are real, but we have to put the derivative here. So that means that this comes down to, we'll pull out the minus I h bar. We got the integral. Remember, our si's were the square root of 2 over L. So I'm going to get a square root of 2 over L sine n pi x over L. Sine n pi x over L. N pi x over L. So there's the psi. And then I'm going to get a derivative of this right here, which means I get another square root of 2 over L, and then a derivative of this. The derivative of this is n pi over L cosine n pi x over L dx. Well, I can pull out the n pi over L, the square root of 2 over L's, and bring all that out in front. And what we're left with is the sine of n pi x over L cosine n pi x over L. And you remember when we did the Fourier series again, that's why that was such an important lecture. The sine cosine was always 0, even when their n and m's were the same. So this is 0. This is 0, this average momentum. But that makes sense because half the time the particle is going this way and half the time it was going this way. And so it can't be going this way more often than it goes this way. So anytime you have a bound state, the average momentum has to be 0. This is going to be true for all bound systems. Okay, the average momentum is 0. But the average square of the momentum won't be 0 because the square is always a positive. So if we just do p squared, well, that's going to be, remember, it's going to be this twice right here. So it's going to be, well, I'm going to get a minus I h bar and another minus I h bar. Minus I times minus I is minus 1 h bar squared. So that takes care of the p doing twice. But this is now going to become the derivative with respect to x of another derivative because it was p squared. So it's a second derivative. So that's just going to be the first and then the second derivative. We get the psi star of x times the second derivative with respect to x of psi of x dx. Okay, and so this becomes p squared is equal to minus h bar squared. Now there's our psi, and then we're going to be taking the second derivative of this. So first of all, we're going to get the square root of 2l with the first psi, and we're going to get a square root of 2l with the other psi, so we can pull out that square root of 2 over l twice. So that just gives me a 2 over l, and then we get the integral from 0 to l. We get the first one, and we get the second derivative of this right here. So we get this first, which is the sine of n pi x over l times the second derivative of this. Well, the second derivative of a sine is still a sine, so it's still another sine of this same thing. I'll write it out over here. The second derivative of this is going to give me a minus a sine of n pi x over l. But every time I take the derivative, I was pulling out an n pi over l, and I have to do it twice because I did the second derivative. So it would be an n squared pi squared over l squared. Okay, well, let's see, what does anything cancel? Well, we'll just, p squared is equal to, well, we got a minus and a minus, which makes it a plus. Good, because we want a positive answer. We can't have a negative. So that's plus. We get a 2h bar squared, 2h bar squared over L. Well, we get an L and we got an L squared. So I guess that's an L cubed. And then we also get an n squared pi squared. And then we just got the rest, which is the sine squared of n pi x over l times the integral of the sine squared of n pi x over l dx. Okay, that looks familiar. It seems like we just did that on the last one. But what did we do? We turned this into a 1/2 times 1 minus, so that's p squared is equal to 2h bar squared n squared pi squared all over l cubed. And we get the integral from 0 to l of 1/2 1 minus cosine of 2n pi x over l dx. Okay, we said last time that this integral is 0. This integral is just going to give me L over 2. So this whole integral is just L over 2. And if I put it together with this p squared is equal to, one of the L's drop out, so that's just an L squared. The 2's drop out, and we get a h bar squared n squared pi squared. So there is your average momentum squared. If we wanted to find the average kinetic energy, we would just divide this by 2m, because p squared over 2m. So if you put a 2m down here, that would just be your kinetic. But you'll notice the kinetic is the same thing as the total energy. Remember, my total energies were right here. Remember, kinetic, this is kinetic plus the potential, but there is no potential inside right here. Remember, U was 0 here. So the kinetic and the total energy are the same. Okay, well that gives me my p squared. So now we can find the uncertainty in the momentum using this equation. The uncertainty in the momentum is equal to the square root of p squared minus p squared. This term was 0, and so all we have to do is take the square root of that. So the uncertainty in the p is just the square root of that. H bar n pi all over L. That would be the uncertainty for every state. You notice as the state gets bigger and bigger, the uncertainty in the momentum gets bigger. Why? Because the energy is getting bigger. If you have more momentum, you're going to be more uncertain. So the very lowest state, so the uncertainty in momentum for the ground state or for the lowest state, that's where n equals 1, that would just be h bar pi over L. And now we can check, because the last time we said that the uncertainty in the x position times the uncertainty in the momentum for the first state, which would be the best you could do. This we said was 0.18 L. This one is h bar pi over L. The L's drop out. And this is pi times 0.18. That's about 0.54 h bar. It's about 0.54 h bar. And remember, I think we said for the two waves, when we had two waves, we said delta x, delta p was around h right here. But it's all going to depend on the potential. Different potentials are going to be different amounts. This is 0.54 h bar. The one that's actually the best is not the infinite well. The best one is the harmonic oscillator, and that's 0.50 h bar. So, but this one's the lowest state is pretty close to 0.50 h bar. It's 0.54 h bar. As you go to the second state, this is just going to grow and grow as you go to higher and higher states. Okay, so there is our uncertainty in the position and the uncertainty in the momentum. And so let's just say you measured. Let's say we measured the energy, and let's say we measured E equals, how about this state right here? Not the ground state, the next one up. We measured 4 pi squared h bar squared over 2ml squared. We measured 4 pi squared h bar squared all over 2ml squared. So we know what n is. N is equal to 2. And we know what the state collapsed into. It used to be, all of them, it used to be alpha 1 psi 1 plus alpha 2 psi 2 plus ... It was all of them. But when we measured E2, this thing collapsed. It collapsed to just psi 2. Right there. So now we know we're in psi 2. That's just as a function of x. If we wanted to add the time into it, well, we already know from right here, to get the full wave function, you just multiply it by the time, where the time is given by this, e to the minus IE over h bar t. So my big psi, if I wanted to know what was going to happen later as a function of time, big psi of x and t would be my psi 2 of x times my e to the minus IE2 over h bar t. Or, we might as well plug it all in what it is, psi of x and t would equal psi 2. Remember, psi 2 would be the square root of 2 over L sine n pi x, but n is 2, so it's 2 pi x over L times e to the minus I, and my e was this up here, 4 pi squared h bar squared all over 2m L squared t. So there it is as a function of time, the wave function, full with x and t, if you were in state psi 2. Now, if we wanted to get the probability of what was going to happen, what do? We multiply this times its complex conjugate. So the probability, which is psi star psi, well, if I multiply this by its complex conjugate, if I just multiply this part by its complex conjugate, it just becomes 1, because e to the minus something times e to the plus something is just 1. So it's the same thing as just this thing squared. It's the same as just psi, little psi, these two right here. It'd just be this squared right here, which was our same picture. Remember when we drew our picture, it looked something like, the psi was like this, but psi squared, psi star psi, would look like, we said it was that one right there. And you notice it's independent of time. This has no time in it right here, so they call this a stationary state. Stationary state. Matter of fact, if you were, so we're saying right there, your stationary state. If you were right there in state psi 3, you'd be in a stationary state, because e to the, you just have a 9 up there, and this would be a 3 right there. Because when you multiply this times its complex conjugate, you get 1. So anytime you're in one of these states, you're in a stationary state. Well, remember from our Bohr model of the atom, when you were in a state like this, you didn't stay there forever. You drop back down to a lower orbit right here. How do we ever drop down right there? Well, suppose right here that remember, we said in general, the state is a combination of all of them. Suppose we're in a mixed state between not just 1 or not just 2 or not just 3, but let's say we're in a mixed state between, say, 1 and 2. 50% 1 and 50% 2. Suppose that psi was 1 over the square root of 2 psi 1 plus 1 over the square root of 2 psi 2. Suppose it's a 50-50. It's not exactly in state 1, it's not exactly in state psi, it's 2. What would it now be as a function of time? That is, what would the big psi be of x and t? Well, it would be this 1 over the square root of 2 psi 1. It would have the e to the minus I e1 over h bar t, plus 1 over the square root of 2 psi 2 e to the minus I e2 over h bar t. So that's the state it would be in. And now, if we multiply this by its complex conjugate, the times won't cancel out. That is, if I take psi star and multiply it by psi, if I multiply this times its complex conjugate, I'll put its complex conjugate underneath it. If that's psi, then psi star of x and t would be 1 over the square root of 2. I don't have to put the star with this because it's real, so it's psi 1. And all it would do is turn that into a plus, e to the plus I e1 over h bar t, plus 1 over square root of 2 psi 2, e to the plus I e2 over h bar t. Now, if I multiply these two together, psi 1 star psi 2, psi star psi. If I multiply these two together, I have to multiply these two first. If I multiply the two first terms together, I get a 1/2. The e's drop out right here, and all I get is that times that, which is just e1 squared, psi 1 squared. Okay. Now when I multiply those two together, I get a 1/2, and I get psi 2 squared because the e parts drop out. But now I get cross terms. I got this times this right here. And so if I multiply these two, I get plus 1/2. I get psi 1, psi 2. E, I can pull the e's out, and it's just e to the, I'll pull out the I. If I pull out the I over, I guess I can just say it's E2 minus E1, E2 minus E1 over H bar T. So that's what I get when I multiply these two. And now I just have to multiply those two together. So I also get a plus a 1/2 psi 1, psi 2. E, when I multiply these out right here, I'll pull out the minus I. And we get, E2 minus E1 again. E2 minus E1 over H bar T. Okay, so this, if I just rewrite this again, we get big psi star, the probability where you're going to find it as a function of time is equal to 1/2 psi 1 squared plus 1/2 psi 2 squared. And then out of these two, I can factor out the psi 1, psi 2. Times psi 2. And I'm left with e to the I something plus e to the minus I something all over 2. Well, remember we said from complex, that's just the cosine function. So that's just the cosine of E2 minus E1 all over H bar T. Okay, so this is the probability. Now the probability is not a stationary state. This thing is oscillating right here at a certain time right here. So it's kind of what the picture of the first one looked like. You know, it's kind of like the first picture would have been looked like that. The second picture would have looked like that. It would be half of this and half of this. Plus, it would be the product, and it would be wiggling around. So this wave would be wiggling around on us. And not only that, if we wanted to get the expectation value of the x position, where's the average position as it's wiggling around? Well, what do? You just integrate psi star x psi dx. That would be the expectation of where you would find it. Well, we already multiplied the two psi's together, so all it would be is if you multiplied all this by x and plugged it right into here, because we already have the two big psi's. Okay, so what does that give me? That gives me the integral of this one, because we're integrating it now, we weren't integrating up here, with an x in there. So you'd have a integral, I'll pull out the 1/2, you'd have an x psi 1 squared dx plus, we have the second one, all we're having is an extra x in there and we're integrating it. So it's just 1/2 x psi 2 squared dx plus the last term right here, we're putting an x in here, and we're integrating it. But the cosine has nothing to do with x, so I can bring that out in front of the integral. Cosine E2 minus E1 over H bar T. And then we get the integral of psi 1 x and a psi 2. Psi 1 x and a psi 2 dx from 0 to L. Okay, well, we've already done this one. This is just the average position when you're in state 1. Well, we already said the average position for all of them is L over 2 right here. So we know this one is just going to give me L over 2 plus a half, so that's L over 4. This is L over 2, because it's true for all the states, divided by 2, so this is another L over 4. Plus, now this integral right here, so you're going to multiply it by this first state times the x times the second state right here. Well, if you remember from electromagnetism, there was something called the electric dipole moment. I don't know, you had it pretty much almost like on the first chapters right here. I think it was something like Q times X, or D, I think they use D, but I'll use X right here. And it was a vector, and it went from the minus to the plus charge right here. Well, this is going to be similar to the dipole moment right here. So let me just call this, I'm not going to solve it, we'll just say, let me just call that P. Well, maybe I want it to be a little p, maybe I'll put a little, it's not momentum. And since this is between state 1 and 2, I'll just say 1 and 2. If it was between any 3 and 4, I'd put 3 and 4 or whatever. It's just between the two states. So this would just be plus P12 cosine E2 minus E1 all over H bar T. Okay, well, I can put these two L over 4s together, and that's just L over 2. So this is just L over 2 plus P12 cosine E2 minus E1 all over H bar T. Well, what would that look like right there? Well, there's your well between 0 and L. This is the average position right here, or the middle of the position. Really, you could say the middle of the charge. Remember, what are my particles? They're electrons or protons. They're charged. So the average position would be in the middle, L over 2, plus oscillating around that with this amplitude. So it would oscillate like this, where the amplitude out to there is P, say 1, 2, right there. Now, if we were to look at this P right here for different initial states and final states right here, remember one of these is the initial one and the 2, it might be the final state right here. If you do this for all of our wave functions, I actually did that over here. For one of these is a 1 and the other one a 2, 1 and a 2, this integral came out to be 0.18 L. That means that this would go back and forth 18%. That would be the amplitude. Go over 18% and back this way 18%. If you went from not only between 1 and 2, say 1 and 3, right here. 1 and 3, then you get 0. If you get 0 out of this, then this doesn't oscillate. The amplitude would be 0 and it would just sit there. You noticed if I went between 1 and 4, it's back to, I get an amplitude right here. And, the only way you can radiate, if you're going to drop from one orbit here to a lower orbit, you've got to radiate wait here. You've got to radiate a photon. And so how do you radiate a photon? You got to shake a charge right here. So this charge has to oscillate right here. So you have to get one of these P's can't be zero. If this P is zero, it's not oscillating, which means I would never see the electron jump from state 3 to state 1. I would never see it drop from 4 to 2. Any place I get a 0 here, it's not shaking. If it's not shaking, it can oscillate. 5 to 3, and so on. 6, it looks like all of these right here, which is all this diagonal is a drop in 2. So these are all drops by 2. It can't happen. This would keep going on forever right here. These would be drops by 4. And you'd have more of them up here. So it looks like for the particle in the box, you have a selection rule. That is, n can never drop by an even amount. That is, n initial minus n final cannot be an even number, even. It'll never happen right here. Also, you'll notice that these numbers, this number, this number, this number, these numbers up here are all drops by 1. Because this is a 2 to 1, 3 to 2, 4 to 3, 5 to 4, and so on. So these are all drops by 1. Drops 1. So they would be coming over to here, where all your energy levels, they would just be like that would be 1. That would be a drop by 1. So these would all be just drops of 1 right here. And you'll notice you get somewhere around 18 to 20% or so, 0.18, 0.19, and so on. You'll notice these ones up here, this one right here, these are drops by 3. Drops by 3. You notice, and this one up here is a drop by 5 and drop by 7 and so on. But you'll notice that this one is about 10 times smaller than this one. This one is 10 times smaller than this one right here. These ones all right here are what's due to dipole radiation. It's the most efficient way to radiate. That's where you just have a plus and a minus, you could think of, and they just swap right here. That's dipole radiation. It's the most efficient way. This one right here, so this is dipole. This one up here is called quadrupole radiation. Quadrupole is when you get 2 dipoles going back and forth. They don't radiate as much. They're much harder, and so it's going to be a much smaller number right here. This one right here is octopole. This would be 4s and 4 charges going like this, and then you'd have whatever, the 16 going back and forth. It just keeps going on and on forever. But the bigger this number is, the shorter the time it takes to drop, because you radiate more efficiently. So these P's, these Pij, is related to the time it takes to drop. It's related to the reciprocal. That is, the time that it takes to drop, time, is proportional to 1 over Pij, right here. So we'll see when we get to the hydrogen atom, we'll be able to see which jumps can't happen, which ones can happen. And so just to show you over here, I'll show a movie. First of all, on the very first movie, I'm going to show you a transition from 2 to 1. And the only thing I've changed there is here, this starts out 100%, it starts out 50% in the 2 states. What I'm doing in the movie is I'm going to start out 100% in state psi 2. So you'll see 2 bumps to begin with. And then the amount in psi 2 will drop, and the amount in psi 1 will start out with 0%. And then as time goes on, this number is going to drop and this number is going to increase. Right here, this one's actually going to go like a cosine, and this one's going to go like a sine. It'll get bigger when you get to pi. And then when you're halfway through, you'll be into this, when you're at, say, 45 degrees. And then later at the very end, you'll be down here. So it's kind of mimicking, starting in state psi 2, then it goes into wiggling, and then you'll end up in state psi 1. Now that's the first one you'll see, and you'll see a little red dot on the screen. The red dot is the average position. The red dot is this. It's oscillating about the middle right here. So you'll see the little red dot oscillate back and forth, and you'll see the wave function start at state psi 2 and go to state psi 1. Then I'm going to show you one with a 3 to 1. There you're starting with 3 bumps. And you'll finally go to 1 bump, and you're going to go wiggling around in between. But one thing you'll notice on this one is that the red dot doesn't move. The average position stayed right there. And which means it doesn't radiate. That's why we got the 0 right there. The 0 is just telling me how much we're oscillating. Then I'm doing a 4 to 1. So you're going to start with 4 bumps, and you'll end up with 1 bump at the end. But here, you'll notice that it's going to go wiggling all around, and it finally settled down to the 1 right here. But you'll notice that the red dot goes back and forth 10 times less than it went back and forth on this one right here. Why? Because this number is 10 times smaller than that one. And then I picked one more over here. I picked 5 to 4. 5 to 4. So you started at 5 bumps, and you ended up with 4. And it wiggled around. The red dot moved quite a bit. It moved even more than this one. It moved 0.2 right here. So what this means is, suppose we come back to here's all of our energy states. And let's say you're in state 6. 1, 2, 3, 4, 5. So we're up here in state 6. Which is the most probable way to get back down to the bottom? Well, if you're in state 6, the most probable way is this guy right here, to 5. And then once you're in 5, the most probable way is to 4. And then to 3, and then to 2. So this thing really favors drops of 1 at a time. Drops of 3 are 10 times less likely, right here. Now, you might ask, how do you get into these mixed states? You know, when you're in state 2, it looks like you're just going to be, that's a stationary state. You'd be there in state 2 forever. And you really would if all it was due to quantum mechanics. But quantum mechanics doesn't explain how you get into that mixed state. It really took quantum electrodynamics to do that. What they had to do is they had to quantize the electromagnetic field. We quantized the energies, but we never quantized the electromagnetic field. Once they did that, then the vacuum is not empty of space. It's due to all these little fluctuations in the vacuum. And these fluctuations can take a state that you thought was stationary, or do we say is stationary, like this, we said was stationary, and it can nudge it into a mixed state. But it took quantum electrodynamics to do that. So what happens is whenever we're in a state, an energy level diagram, you might be in this stationary state, but then the vacuum of space kind of puts you into a mixed state between this one and say this one. Now you're in a mixed state, and you emit the photon, and then you go down to this state right here. So that's how we call that spontaneous emission. Spontaneous emission. Okay, but it took quantum electrodynamics to explain spontaneous emission. Right. Now, if you go to Canvas, on Canvas, into Files, there is a PDF file that of all of this from Mathematica. You might take a look at it, and because if you take quantum mechanics later on, you're going to be doing the infinite well. And in that PDF, I kind of beat it to death and calculate everything we've done in the last 2 lectures. So go on to Canvas, go to the files, and there's something in there about the infinite well lab. Okay, hopefully this is starting to look a little bit closer to the hydrogen atom.